Hey everyone, welcome back to Camp Fiveable. If you're new here, hi, my name is Sumi. I'm teaching this calculus course mainly for students who are going into AB or BC next year. And this is just kind of a course to not necessarily get really good at solving problems, but to understand why calc and math works the way it does and how we can solve it. And before I go on, good news, I got a 5 on my Calc BC exam, so I am in fact qualified to help you out in this area. And yeah, let's pull up the slideshow. How are all of you doing? I'm good, but I'm like really tired. I just got back from Kenneth, you're tired too. I just got back from a 2-week-long debate workshop, which was like really intense, but it was really fun. So if you have any questions, feel free to reach out, and I'm happy to talk to you about that as well. Today's lesson is going to be maybe on the more difficult side, one could say. I'm going to be going over a lot of topics, but I'm hoping that they will get easier. I'm trying to figure out my setup, as always. Perfect. All right, let's pull up the slideshow, shall we? Okay, again, welcome to Camp Fiveable. This lecture is going to be on the applications of derivatives and integrals. So it's going to go pretty fast. I'm going to teach you a lot of concepts, but I'm hoping even if you don't catch everything, it'll give you kind of a general idea of the ways in which derivatives and integrals can be used in calculus. Yeah. So my name is Sumi and I'm a rising junior. I live in Colorado. And yeah, on the side, I'm really passionate about the environment. So I have my own organization called Project Planet Advocacy. Be sure to follow the Instagram. Yeah. And then upcoming classes, the 20th will be integrals and volumes. This is a BC topic. The rest of the topics after here on out are going to be BC topics. So this is my last AB topic. So if you're taking AB next year, you're welcome to watch my other lectures, but I will be switching to topics that will only be on the BC exam. So yeah, just keep that in mind. Integrals and volumes, polar and parametric, and then convergence and divergence of series, and also Taylor series within that. And I think I've had 6 or 7 lectures right now, and these are kind of the main topics of the BC class. So if you've been staying tuned throughout all of my lectures, you will basically have covered the entire BC curriculum this summer. So congratulations if you stick with me until August 17th. You'll have a really good head start on the other kids taking BC calculus or AB. Just quick review if you haven't been with me in my other lectures. First is the power rule. that simply states that, oh, and by the way, I'm going to go through this really fast, but if you have questions on any of the topics, just let me know in the comment section and I will slow down and explain said concepts to you. So just reach out and I can let you know. So the power rule, that looks kind of complicated, but it just says that if you take the derivative, then you take the exponent of that that function, you put it in the front, and then you subtract 1 from the exponent. So the derivative of x cubed would be 3x squared. The derivative is the slope of the tangent line. Remember this. This is really, really important. And it is also the instantaneous rate of change. The fundamental theorem of calculus says that integrals and derivatives are opposites, and you can use integrals to determine the area of the curve. And you can set the derivative to 0 to find critical values, so maximums and minimums. And then when the derivative is positive, the function is increasing, and when it is negative, it is decreasing. Cool. Just to give you like a little more insight into that, the second derivative gives you concavity, so positive is concave up and vice versa, and then the point of inflection will be where it changes from concave up to concave down, or in other words, where the second derivative equals 0. So you can see in my little diagram, when it's decreasing, the derivative is negative. The derivative is 0 at this minimum point. It'll also be 0 here and here. The point of inflection is where it changes concavity, and yeah, the second derivative is positive when it's concave up. Awesome. We went through this really, really fast. Okay. More important derivative formulas: product rule, quotient rule, chain rule, and trig rules. Yeah, those will be important. But you'll have plenty of time to memorize them before the exam, so don't worry about it if you don't have them memorized right now. I'm sure you'll do a lot of practice problems, and they'll just become second nature to you. Cool. And then recap on integrals. The anti-power rule says that when you have the derivative of x to the n, the integral would be x to the n plus 1 over n plus 1. U-sub, you can substitute any expression for u as long as you also calculate du. And then here's an example of that. Do you want me to? I'll go ahead and solve this integral on the board. Cool. So we've got, oh my god, where's my marker? There it is. We've got, we've got from 1 to 0, x squared plus, or x squared times 1 plus 2x cubed to the 5th power times dx. This marker is running out as well. Let me go find it. Let's see. Dx. Cool. So let's think about how we want to substitute this. So first, u is going to be 1 plus 2x cubed. Okay, and we have du is 6x squared. All right. So if you plug all of that in, we've got from 1 to 0, x squared. Actually, just got 1 to 0, u to the 5th, du, and then we've got over 6, right? Because this is supposed to be 6x squared, and we only have 1x squared. And that's going to be 1/6 times u to the 6th over 6, which equals 1/6, 1 plus 2x cubed over 6, right from 1 to 0, and that's going to equal 1 plus 2x cubed over 36, 1 to 0, and that'll simply be, right, we're going to plug these in, 1/12 minus 1/36, we got 1 over 18. Does that make sense? If it doesn't make sense, please let me know because I can definitely explain stuff. And yeah. All right, so now let's move on to today's topics. We have a lot to get through, but it should be pretty fast, pretty easy. Maybe not easy, pretty fast, and they all kind of link together. So I will say that even though we have a lot of slides and a lot of topics and a lot of things that we're learning that are new today, yeah, they should hopefully click in your mind. And if they don't, again, please leave a question in the chat and I will be sure to explain it to you. So the first concept that we're going to go over is optimization. So we use derivatives to find the maximum and minimum of functions, and we can do the same thing to find the maximum and minimum of other values. Implicit differentiation can be important. I don't think we're using any implicit differentiation in today's problem, but it can be important. And our example is find the maximum volume of a cylinder inscribed in a sphere with radius 10. All right. Can all of you see that okay? Cool. So the first thing that we're going to look at is just draw a little picture. Pictures can be really useful. And I'm just going to draw a picture of a cylinder inscribed in a circle, which is going to represent our sphere. Okay, so we can get a few values from the problem. We can get 1, right? And that is this distance, right? Which is going to be, right, it's going to touch the middle, and the corner of the cylinder is 10. Okay? And we can use the Pythagorean theorem and just say value is going to be x and this value is going to be r. Okay? And based on that, we can say x squared plus r squared equals 10 squared, right? And x equals the square root of 100 minus r squared. All right, is everyone still with me? Cool. So now that the volume of a cylinder, in case you don't know it, is pi r squared times h. Okay. Cool. At least one person understands. So now let's think about this. If we want to maximize the volume, based on what we've learned about derivatives, we can say that a maximum volume means that the derivative would equal 0 at some point, right? So we need to take the derivative of this. But first we can't take a derivative if there are 3 values. Plug something in. So based on our handy little picture here, we can say that the height of the cylinder is 2x, right? So we got from the center of the cylinder up to the top, and then we got one more. So we can say V equals pi, actually I'm going to just draw this in here, equals pi r squared times 2x, and we know that x equals the square root of 100 minus r squared, so we can say pi r squared times 2, 100 minus r squared. And I just want to clean this up a little bit, so I'm going to say 2 pi r squared, 100 minus r squared. Okay, so now what we want to do, now that we have an equation, is we can take the derivative of this equation. So we can say dv over dr equals 2 pi, and now we have to use the product rule. And I can calculate it. You would kind of hopefully catch onto this, but I'll calculate the derivative for you in this case, and I can think aloud. So 2 pi, first we have to take the derivative of this. So this is going to be 2r 100 minus r squared minus, right, because we're going to get a negative value here, minus 2r over 1/2 100 minus r squared times r squared. Okay? That's how you would calculate the derivative. And that looks really, really complicated, but we can make it a little bit simpler. We can say 2 pi times 2r 100 minus r squared minus these two goes away, r cubed over the square root of 100 minus r squared. And like we found earlier, this is what we're going to calculate when r equals 0, right? Because we want to find a maximum value. So that equals 0. 2 pi off. And then we're going to multiply the entire thing by the square root of 100 minus r squared. So we've got 2r times 100 minus r squared minus r cubed, which in turn equals 200 minus 3r squared equals 0. So we got r squared equals 200 over 3. Does that make sense what I did there? Yeah. Okay. Perfect. So now we've got to find the volume, right? So we know what R is. We have V equals pi R squared H, or in this case, R squared 2x. And we know that R squared equals 200 over 3. So in order to find x, we can say x equals, right, we're just going to plug it back into this equation, 100 minus r squared, 200 over 3, which equals 100 over squared. So we can say 10 over root 3. We want to simplify it. So our volume is going to equal pi times 200 over 3 times 10 over root 3. And to simplify that a little bit more, we've got 2,000 pi over 3 root 3. And that is the maximum volume of a cylinder inscribed in a sphere that has a radius of 10. And if you don't understand this, don't worry. I never actually understood optimization till like maybe March. I hope that helps with the glare a little bit. Okay, that's a little bit better. Till maybe March, so don't feel that if you don't understand it, you're never going to understand it. It took a lot of time, but this is just kind of an introduction. Now, this reduces the glare, but it makes it very grainy. I think we're just going to have to live with the glare. I hope that's okay. Cool. So now onto our next topic. Rectilinear motion. So there are a few things that you need to understand about rectilinear motion. The most important things are that if you have a position equation, it'll usually be x or t of y or y of t. And those simply mean that x of t means that the particle is moving from right to left, and y of t means that the particle is moving up and down. And so we have the position equation, we have a velocity equation, which is the derivative, right? Because it is the rate at which the particle is moving. So that will tell the speed of a particle, and the acceleration will tell the speed at, or the rate at which the particle is kind of changing. So basically the amount of change of the speed. So if the acceleration is, or if the velocity says that it is moving to the right and it's saying it's speeding up, that means and the acceleration says that it's positive, it means it's going to be speeding up. All right. And this will make a lot more sense when we do an example. So our equation is x of t equals 2t cubed plus or minus 21t squared 60t plus 4. Perfect. So first we want to find goal is stopped. And if we analyze that sentence, that means that when it's neither speeding up or slowing down, it's 0, which is essentially when the velocity is 0. So first we need a velocity. And the velocity is going to be the derivative. So v of t, and you can do this with me, it's just a power rule. It's going to be 6t squared minus 42t plus 60 equals, which means that we've got 6t plus, or t minus 2, t minus 5, which equals 0. So thus at t equals 2 and the particle is stopped. Cool. You know what I need? I need a chalkboard. Then we won't have issues with the glare. Maybe I'll like buy some chalkboard paint and just paint over the whiteboard. Then is it moving at t equals 3 seconds? So I don't know why I erased this. So at t equals 3, we want to say which direction is it moving. So that means that we need to find the velocity. So v of t equals 6t squared minus 42t plus 60 and where is it moving? In which direction is it moving? So we essentially want to figure out whether it is positive or negative. So we've got 6t squared minus 7 plus 10 equals 20. 10 is a number. It's moved. And the left hand have it. Cool. It's t that's position. So it gives 2 plus. And if I all that minus 189 plus 180 plus 4, that'll be 54 minus 9 plus 4, which is 49. Okay. So the next question is, what is a of 3? So a of 3 is acceleration. So we first need to find the velocity. And then the acceleration. So we just do that over again. 12t minus 42. And then we're going to substitute 3. That's 36 minus 42 equals -6. And if you recall, the velocity was a negative number, so is the acceleration. So we know that it is speeding up. All right. Does anyone have any questions about rectilinear motion? Cool. And then a few more things about rectilinear motion that I just want to touch on. I'm not necessarily going to do any practice problems on it, but just so you guys know that when it asks you to find displacement, that is a change in position. So it'll usually give you the velocity and then it'll ask you to find displacement. So you can just take the integral. But if it asks you to find the distance, then you need to take the absolute value of the velocity. So in essence, right, if you have a car and it moves a little bit to the right and then it moves a little bit to the left and then it moves like a little bit to the right, you have to add up all those values to find the distance that it traveled. But if you have a car and it does the same thing and you just want to know kind of the displacement, then you can just measure the displacement directly. And the way that you find the integral of an absolute value function is you need to split up the negatives and the positives. And I will show you this on a graph really fast. And what that looks like is, say I have an equation that looks something like this, and I want to find the absolute value, right? I can take the function, say it's f of x, and I need to find this value, and this value, and this value, and this value, and then I'll split it up. So I'll say from b to a, the value of f of x, and now this is negative, so I'm going to need to compensate for that, so minus from c to b, f of x, and then plus, right, this is positive again, b to c, f of x, right, etc. And then if you add up all of these, you'll find the distance or the absolute value or whatever you're trying to find. And this also is valid for areas. So if it says it wants you to find this entire area, if you just find it from D to A, it's going to be these two areas added up, and this is going to be negative. So if you need to find an area, you're going to have to use this same method. Pretty basic, but I just thought I'd spell that out. And I don't know if that's a question or what that is. Okay. Cool, on to the next thing. we've already learned so much. This is like 2 months of school that I just taught you in like 30 minutes. So if you're understanding this, you are going to be just fine in whatever calculus class you're in. Next is, this is a really easy concept. And it just says that two rates can be related to each other, right? We have two things moving in junction with each other, right? Like the radius of a cube or of a circle and circumference of the circle, right? We know that if the radius increases by so much, the circumference is going to increase by so much. So that's, I guess, the theory in calculus that we're experimenting with over there. And then, yeah, implicit differentiation is important for this too. So I'm just going to show you a really, really simple example. So there are obviously going to be harder examples, but this is just to adapt. So it won't be as hard as optimization. And then drawing pictures is also really important, especially when you get to more complex problems with lots and lots of different variables. And so our problem here is if we have a cube, right, with side length of s, right, find the change in volume as it relates to the side length of s. So we know that the volume is s cubed. So like I said, you're always going to use a t per time. So the change in volume as it relates to time is going to be, and you're going to use implicit differentiation, 3s squared ds over dt. And then, yeah, you can do some cool stuff with that. So any related rates problem is going to stem from finding an equation like this. And then you can go from there. But at its most basic form, that's what a related rates problem is going to be. And then sometimes it'll have you plug in variables. So it'll be like, you know, the volume is changing at this rate, so you can plug in a value for this, and the side length is this, and then it wants you to find ds dt. And that's just simple algebra and plugging in stuff. Cool. Accumulation. So if you're given the velocity, finding the integral will help you find the area or how much volume or value is accumulating. And so if you think about driving a car, for example, you're going to have kind of lots and lots of different lines that represent how fast the car is going. And I'm more in my integrals kind of lecture, so if you are more curious about how it works, be sure to check that out. But for now, I'll just tell you that if you're giving a rate, finding the integral will help you accumulate values. So if I say the rate at which, actually, let's use that problem. And you'll get these problems a lot, especially in your FRQ section. So I'll say the rate at which a water is flowing out of a tank is f prime t equals negative x squared plus 3x minus 7. Okay? And so, I don't know if these would be t's. Let's pretend these are t's. T, 3t minus 7. Okay. And so, let's let's pretend that we want to find the amount of water that has flown out of the tank after 10 hours. So at time equals 10. So we've got the integral from 10 to 0, negative t squared plus 3t minus 7 dt. And we can find the integral of that pretty easily, negative t cubed over 3 plus 3t squared 7t. And then plug in 10 for that. So we're going to get negative 1,000 over 3 plus 300 over 2 minus 70. And then you can figure that out on a calculator, and that'll be how much water has flown out of that tank after 10 hours. So yeah, that actually concludes our lecture. I hope this made sense to everyone. If you don't, feel free to contact me. You all have my email, I'm assuming. If you don't, I can give it to you. And yeah, if you guys want to talk about anything else, debate camp, the environment, anything, school, AP, feel free to email me about that as well. And I hope you have a nice week. I'll see you next week. Bye.